Okay, here's the last lecture for the day. This might take a little bit of time, but I figure, hey, what the heck? We've got, guys have anything better to do now that you've all given your speeches. So, let's do a little bit of review here. Okay, if we drew, so here's a magnetic field, and if we have a charged particle moving through our magnetic field, okay, the force acting on this particle equal to Q V cross B. Okay. Then we have a different magnetic field, and we'll turn this one and put it on end. And through our magnetic field, we have a wire, okay, with a current going through it. Okay, this distance here, we'll consider that a length L, and this gives us a force. Oh, and this is still B. That's a displacement vector L. That's going to equal I L cross B. And that's for the current in the wire. That is the force on the current in the wire. All right. And from the lecture before last, if we have a loop of current, with current going that way, and this is length A and length B, okay, this will have an area A pointing out that direction. This will experience a force coming out of the page here and going into the page, here, and this will give us a torque, and our torque is going to equal I times the area times the magnetic field, and we called this the magnetic dipole moment. Okay, that's the magnetic dipole moment, and that has given, which changes this to, instead of tau equal I A times B, okay, our torque equals mu cross B, because IA became our, okay, that was our mu for a magnetic dipole moment. Okay, so that's a real quick review of how our fields work, and that they're all pretty consistent so long as we are thinking in this three-dimensional vector world, because we haven't really had to do that a whole lot before, and now we really do. All right, so, and the only way, so we're going to change gears a little bit here. And the way we've talked about our magnetic fields here is we have this north pole magnet and a south pole magnet. And we've mentioned that it has this magnetic field that runs north to south. Okay, and it's got loops and stuff. All right. However, we haven't really talked about what caused it. What causes the magnetic field? So let's go back and look at some of our other fields that we've dealt with before. We've had gravity. Okay, gravity from a massive particle, we know comes from, is a characteristic of the mass itself, and we'll have a little, we have a little test mass, call it m naught, and this is m, and all around it we have this field where G, okay, which is our field due to gravity, is equal to big G m over r squared, because how far, it's a function of how far it goes away, with an attractive vector r hat, meaning that it's going to be attracted to the center of the object. Okay. Then we have an electric field. Okay, our E here, which is given by, okay, and this occurs with charges. It's the charges themselves that actually create our electric field. And then if we have a particle inside of this, okay, it's going to move in that direction. And the field, the force that it experiences based on its position, okay, is E which equals Q over r squared, so it's proportional to the charge on this particle and the distance away from the positive charges, times r hat, because it's away from the positive charges, but it also has this constant of proportionality, just like this one had a constant proportionality g. Okay, well, that brings us to our magnetic field. What happens in a magnetic field? What is the cause? What is really the cause of the magnetic field? Okay, well, for magnetic field, we have these lines, and we have our particle that moves like that, and it's going with a velocity. Okay, and it has a charge, and this is B. Okay, so what is the charge, or what is the cause of this magnetic field? And it winds up that the actual cause of this magnetic field is other moving charges. Other charges will move and create this magnetic field, and so we experience a force by one charge moving across a field that is created by other moving charges, just as over here, okay, this electric field makes this charge move because of other static charges. This gravitational field makes this mass move because of other masses that are emitting gravity. So it's very consistent in that regard, as far as our idea of fields. That here's a moving charge, and this field is caused by the motion of other charges. Okay, which brings us to Biot-Savart, the Biot-Savart law, and I could say it with my John Cleese, my Biot-Savart. Okay, or my Peter Sellers Inspector Clouseau, but that's lost on you guys. So, here's the Biot-Savart law, and this is it's kind of a cumbersome equation, but when we break it down, we analyze it, this will actually make a fair amount of sense to you guys. So, except there's a fair amount of math involved. Here's the idea. So we're going to have a current of wire. All right, and that's our I. Okay, along this wire, we have apart from the start, we have a point P out here. We'll call it P. Okay, and our point P, we want to know what the magnetic field is in this amount of space right here. And so what these guys figured was, along here we have a infinitesimal distance. Okay, it's actually a differential current, but we're going to call it D. That is our ds as we move along our line. All right, and they discovered that the magnetic field here is going to have to do with the amount of current going through the wire, so that if the current increases, okay, then our magnetic field will increase. That the direction of our displacement is also going to affect this. Okay, and the other thing we've discovered is that along here, okay, we have a distance r. And so along that distance r, we have an r hat. Okay, and the magnetic field from this amount of motion of current, an infinitesimally small amount of moving charge, is still a moving charge. And that's going to create a magnetic field, a teeny tiny magnetic field, at this point that by now you should recognize is going to be affected less and less according to r. In fact, it's going to be according to r squared, which should make sense. That it's one of these, this inverse square law is a pretty standard concept throughout physics and throughout all of science. And this is what they came up with, so that this going to create this infinitesimal change in our magnetic field is going to be given by our current, okay, times our differential distance along the line, divided by r squared, and it's going to act from the current out to that field, and so that's going to be with r hat. However, just as all the other ones did, just like this one had a ke, and just as this one had a g, this one also has a constant of proportionality. Okay, and this constant of proportionality is kind of funky. Okay, it is given by this. Mu naught divided by 4 pi. And the interesting thing about this is that this is an exact value. Okay, it has an infinite number of significant digits. Its value is, well, this mu naught here is equal to 4 pi times 10 to the negative 7th. Well, we'll get into the units of that in a minute. This mu naught is called the permeability of free space. It is the permeability of free space for that particular mu naught. Okay, and what this really means is that this is a measure of how easily a magnetic field flows through free space. So what are the units of this going to be? That if this has to cancel with all of these to give us magnetic field. Well, magnetic field is in units of Tesla. So that's what we want to wind up with. But we want units that are going to cancel out with what we have here. Well, a ds is a distance. And we have an r here on the bottom, so that's meters divided by meters squared is going to give us a meter on the bottom, which means we want a meter on the top. So that's going to be times meters. And then we have a current, and so that's going to be per ampere. And the reason this is exact is that this is actually how our magnetic fields are defined. This defines the strength of magnetic fields is based on this particular value. 4 pi times 10 to the negative 7th Tesla meter per amp. And so that's how this becomes an exact value. All right, but of course, these are differentials. These are not really what our B is. We want to find what B is. And so B okay, we're going to have to integrate dB, and we'll have to integrate this. So we're going to get this times, and if we integrate this, we'll have all kinds of constants. We'll have mu naught. We're going to maintain I as a constant. We're not going to, it'll always be a constant current. Divided by 4 pi times the integral of ds cross r hat. Okay, in fact, that's what I missed up here. Is that this is going to be cross r hat, which should make sense. That if the current's in this direction and r is in that direction, it's going to be ds cross r hat. That's going to make this point The magnetic field in this point is going to be in that direction. It's going to be coming up out of the page. It's going to be ds cross r hat, because this is a vector. Okay, divided by r squared. Okay, and this is, well, so that's that. Then we integrate it, and b becomes, well, that's what b equals. So b then equals mu naught I over 4 pi integral of ds cross r over r squared. And this is our cloudy equation that you guys are going to need to know. Okay, so we're going to do a couple of examples here. So we're going to stop here, and that's the end of the BIOS of our lecture, or BIOS of our lecture, but then we're also going to do a couple of examples in the next couple videos. So here we go.